Today we're going to tackle chapter 7 and 8. One has to do with measurement, the other has to do with research design. Um, One of the things about your proposals that I want you to do, the reason I want you to do proposals is because this teaches you how to put a proposal together, and that's really what research is all about. Some things it's not ethical to do research on select things, or to manipulate people or objects the way that you might potentially do that. And for this reason, in order to understand research, we need to understand what you can and can't do. So one of the reasons we're doing these proposals is so that it teaches you not only how it's done, but why it's done, and the structure of the proposal. So let's go ahead and get started with today's lecture, or this week's lecture, actually. We're going to start with chapter 7, of course. Uh, Measurement is defined as a procedure whereby a researcher assigns numerals or other symbols to the empirical properties of variables according to a prescribed set of rules. Three basic concepts to define measurement. Numerals are symbols that are given quantitative meaning and then become numbers that make possible the use of mathematical and statistical techniques for the purposes of description, explanation, and prediction. Now, one of the reasons that we're talking about numerals is because a lot of times especially in psychological research, we want to quantify things as much as we possibly can. But when we're talking about, how angry were you on a scale of 1 to 10, how angry were you? What we're doing is we're assigning numbers to feelings, or assigning numbers. Well, in my own research, we assign numbers to resilience, to how strong somebody's resilience was. We assign numbers to how culturally aware an individual was. And so that's really what we're doing. And some of this is a little superficial. Can you really assign a number? Well, they do this all the time in the hospital. They ask you on a scale of 1 to 10, how bad is your pain? Well, you experience pain one way, and I may experience pain a totally different way. What might be a 9 to you might be a 3 to me, or vice versa, of course. It really all depends on your experiences. But here we are. We're in psychology. We're dealing with psychology, and medicine's the same way. We're trying to quantify something that is doesn't isn't represent shouldn't be represented by a number. If if I hurt myself, is it an owie? Is it an ouch? Or is it a scream? That's pretty much it. And if I scream, will it get better? And the answer is probably yes, because it will block some of the pain messages going to my brain. But so we're talking about numbers here. We're talking about assigning numbers to things that that shouldn't be shouldn't be quantified, or it's difficult to quantify them. I mean, we do it, and we do it all the time. In With Beck's depression inventory, of course, we're putting a number to how depressed you are. Assignment refers to the mapping of symbols onto objects or events. Rules explicate the ways in which numbers or numerals are to be assigned to objects or events. And this is something that you need to think about. I know this doesn't make a lot of sense. Mathematicians and scientists go a little berserk when we start talking about psychology being quantitative. But the reality is, this is about the only way that we can do it, and make the research as useful as we possibly can. Rules are the most significant component of the measurement process because they determine the quality of the measures taken. The function of rules is to tie the measurement process to reality, and that's really what we're trying to do. We're trying to create a situation where we're actually dealing with reality. So, and that's one of the reasons why um, uh, when the resilience scale was put together, why they did it quantitatively. They had to do it quantitatively because they needed to say this person is more resilient than this person because of this question here, and they answered this question this way, and they got optimum points. And they answered somebody else answered the question this way, and they got lower number of points, and it showed that they weren't as resilient. So we need rules. We need to state those rules, and usually that has to do with whatever survey instrument that you're using. It will create the rules to tell you how you measure this or that or the other. If we're talking about depression, of course, how do we what are the rules behind defining depression? And of course, there are ways to quantify these things. Isomorphism is a mathematical term that means similarity or identity of structure. In determining whether a measurement procedure is isomorphic, the central question concerns not just the degree of congruence between the particular numerical system that is being used in empirical reality, but also the concept being measured. Social scientists measure indicators of concepts, and often multiple indicators must be developed to represent abstract concepts. And this is what we had to do with resilience. Um, how in the world how in the world do we even define this? And of course, this needs to happen before we can do the research. Uh, does resilience mean that you survived? Well, that means everybody that's alive would be resilient, but that's not really the definition of the term. We need to we need to define the term. We need to put it in context so that it has meaning. Indicators are terms used to refer to a concept. Indicators should be grounded in both theory and empirical observation. Indicators are used to measure a concept. They should derive from theories and practices of concept. And of course, this is the uh, the picture on the right shows a concept indicator to refer to concepts. Yeah, we're talking about economic giants. We're talking about these three countries: Bangladesh, India, and Vietnam. India, Bangladesh, and Nepal. Um, Life expectancy for the three countries, it looks like Vietnam has the highest life expectancy. Infant mortality rate, India has the highest infant mortality rate per 1,000 births. Access to improved sanitation. Bangladesh seems to have access to improved sanitation. Mean year of schooling, they're all about the same. For Pakistan has more education. Female literacy rate, as you can see, India has the lowest. Myanmar, which used to be Burma, and Bangladesh have a higher female literacy rate, and of course the male literacy rate is higher in Vietnam than Myanmar or in India. So, which is the economic giant? And from this, you would have to say that India is not a very strong country, but the reality is, of course, they have over 1 billion people and they produce a lot of goods. So does that make them an economic giant? Well, they have other problems, as you can see. Life expectancy is kind of low. Wait a minute, what is this? Oh, in Vietnam, I'm 71 right now. I'll be 72 in October. I'd have 3 more years to go. In Bangladesh, I'd already be dead, and so I'd already be dead in India as well. Wait a minute, is that right? Yeah. The concept of democracy can be represented by several different indicators. The fairness of elections, and of course that came up in the last election. The degree of competition between the political parties, and of course there's a lot of competition right now. The freedom of the press, and of course that was there was an attempt to stifle the press. Evidently, they were trying to figure out where all the leaks were coming from, and they were looking at reporters' telephone records. CNN got hit. Washington Post, New York Times, they were all hit. So in the last administration, the freedom of the press kind of took a dip because the federal government was trying to crack down on the liberal press. But of course, that has to do with democracy as well. The freedom to organize, and of course, that's something that we have in the United States, and the rights of minorities. And this is with the new holiday, Juneteenth. Juneteenth is the 19th of June. It was the day that the slaves in Texas learned that they were free, and there was a big celebration, of course. And I would imagine there will be a big celebration. I've actually attended Juneteenth celebrations in Oklahoma. I'm not black, and not. I certainly my family weren't slaves. They were indentured servants, but they were never slaves. But we attended them way back in the '90s, the early '90s. So it's something that we've been aware of. My family has been aware of since for 30 years, and now it's a national holiday. So it'll be a time to celebrate, whether you're time to celebrate freedom, whether you're black or white or native or Hispanic, I guess. Four levels of measurement. There's not the nominal level, the ordinal level, the interval level, and the ratio level, and we'll explain them all right now. The nominal level is the simplest level of measurement. It functions solely by the purposes of for the purposes of classification. Symbols are used to classify objects or events into categories. Nominal level is used when the properties of a variable can be classified into a set of categories that are both exhaustive and mutually exclusive. And examples: what is your gender? Are you male or female? What is your hair color? And you can write lots of different colors there. Ordinal level measurement allows for classification and also degrees within the classification. Examples: productivity, socioeconomic status, democracy, intelligence, education, and motivation. We have IQ tests. People talk about what their IQ score was. Well, that's an ordinal level of measurement. Whenever a phenomenon or process has a range, such as greater than or less than, highest to lowest, etc., you have an ordinal measurement. How do you feel today? Happy, unhappy? How satisfied are you with our service? We see these surveys all the time. Interval levels of measurement rank a set of observations in terms of the relation and also the exact and constant distance between each of the observations. In addition to saying that one object is greater than another, you can now specify by exactly how many units the former is greater than the latter. Interval data need a precise unit of measurements. Examples: income, intelligence, scholastic aptitude test scores, voter turnout, and crime rates. There's a definite number. Voter turnout rate in the last election was the highest that it has ever been. We had more people vote in the last election. And what is this? Prevalence of anemia in children under 11 years of age in Mexico in 1999. You can see all the numbers. Ratio level data are variables that have absolute and fixed natural 0 points that can be measured. A ratio level of measurement is achieved only when it is possible to attain all four of these relations: equivalence, greater than, known distance of any two intervals, and a true 0 point. In social sciences, this might translate into the length of time migrant workers typically stay at a single job site, number of community affiliations, number of occupations held by a certain age, Examples, your weight, you can be zero, have an absolute zero. Time, when I started at Dene College was, when did I start? 2016, in August of 2016. Due to the precision of the numerical measures used on the ratio level, highly powerful statistical manipulations can be performed on these values. So when we're talking about something that has an absolute level, that means that there is a zero. Uh, the the answer can be zero. With a number of traumas in your life, of course, you can have had none, but you could have had gotten spankings every day for a year. That's 365. What are we doing here? Oh, this is the people that are Republicans and Democrats. As you can see, there are more Democrats than Republicans. Democratic Party seems to be a little bit more inclusive. It's not that much. Well, 11%. That's quite a bit of the population. Variables that can be measured at the ratio level can also be measured at the interval, ordinal, and nominal levels. As a rule, properties that can be measured at a higher level can also be measured at lower levels, but not vice versa. Differences in scores that are due to anything other than real differences in the aspects of the property being measured are termed measurement errors. Common sources of measurement errors: the scores obtained may not be related to the attribute the researcher intended to measure, but to another associated attribute. Temporary differences in conditions such as health or mood, which may affect a person's response or behavior. Differences in the setting in which the measure is used. Differences in the administration of the measuring instrument, poor lighting, noise, tired interviewers, differences in processing. Different people interpret the measuring instrument in different ways. And of course, anytime you get two psychologists in a room together, there will probably be a disagreement about about something. Systematic or random errors. Systematic errors occur whenever the measuring instrument used consistently introduces a degree of invalidity to all findings. That's a systematic error. Random errors, by contrast, affect each instance of the measuring instrument's use in a different way. So systematic errors, for some reason, my Fitbit, when I was living in Saley, thought that I told it I was living in Arizona, and it thought I was living in Phoenix. And Phoenix, of course, is on Pacific Coast time, and Saley is on it's on Mountain time. So, and this isn't that funny, but every time I looked at my watch, I had to either add or subtract. I had to add an hour or subtract an hour if I was talking to somebody from Iowa because they're on Central Time, and if I was talking to Marius Begay lives in Snowflake, and Snowflake is on Phoenix time or Pacific Coast time. So I had to add an hour. Wait a minute. He was an hour behind me. Yeah, he was an hour behind me. Anyway, so there you go. Systematic errors. So my watch was always wrong, no matter where I was, since it was set on Phoenix time. So I knew what time it was at Marius's house because my watch always told me what time it was in Phoenix or in Los Angeles for that matter, or whatever. But I always had to do the math, which wasn't a lot of fun. If I was talking to somebody in Iowa, of course, I had to subtract 2 hours, or I had to add 2 hours from what my watch said. The seriousness of the issues of validity and reliability prompted the development of techniques for reducing measurement errors. So we do get errors. There are numerical problems, and we can use statistics to take care of those problems. Validity is concerned with the question, am I measuring what I intend to measure? The problem of the validity of the measurement is the outgrowth of the nature of the variables studied. There are three basic types of validity: content validity, empirical validity, and construct validity. Now, let me give you a quick and easy example. When we were measuring resilience, I had to find an instrument that actually told me what people's resilience was. Well, it's easy. Well, and the question is it a valid test? Was what I used a valid test? And there are several different resilience scales out there, and I had to find one that I thought would be accurate. I had to find one that I thought was valid, and there are tests out there that aren't valid. One of the ways that you can select a good instrument to use is by how often was it used in the past by other researchers. And of course, I found one that hadn't been used a lot by other researchers, not that much anyway. But I thought it was more accurate for the population I was going to study. Another question was cultural level. How in the world do you judge somebody's cultural level? You ask them if they go to powwows. What are you doing? Well, there was a instrument that was developed at UCLA, and the lady used standardized the test, or the instrument. She standardized the instrument with the student population that she had at the time. Where there was a large Hispanic population, there was a moderate African American population, and there was a large white population. There were also natives. There are natives that live in California. There's If you talk to Dr. Kine, she used to teach at San Diego State, and she'd tell you about all the reservations around San Diego. Yeah, so there's a number of natives that live in that area, and actually it was standardized with those individuals as well. So that's the instrument that I used. So we'll talk about content validity, empirical validity, and construct validity. So that's what I was looking for. I wanted to make sure and the other thing that I needed to make sure was that it had actually been used by other people with this population, and they determined that it was accurate. And not the easiest thing in the world, because there aren't a lot of there's hasn't been a lot of research using on American Indians, no matter where you are, whether you're in California, Arizona, Washington State, Oregon, Wyoming, North Dakota, or Montana, or South Dakota. Content validity, the measurement instrument covers all the attributes of the concept that you're trying to measure. There are two common types of content validity. Face validity rests on the investigator's subjective evaluation of the appropriateness of the instrument for measuring the concept under study. The main problem is that there are no precise, replicable procedures for evaluating this type of content validity. It is difficult to repeat the evaluation procedure precisely. Then the researcher has to rely entirely on subjective judgments. And of course, that's what I did. So my resilience test had face validity. Sampling validity, the researcher develops an exhaustive list of all domains of the concept under study, then develops a measurement instrument, for example, a questionnaire in which each of these domains is represented. Ascertaining sampling validity serves an important function. It calls for familiarity with all the items describing the content population. And of course, my instrument had content validity. Empirical validity is concerned with the relationship between a measuring instrument and the measured outcomes. Scientists assume that if a measuring instrument is valid, the results produced by applying the instrument and the relationships existing among the variables measured in the real world should be quite similar. If a measuring instrument is valid, then there should exist strong relations between the results produced by the instrument and other variables. An example would be an educator seeking proof that the IQ scores of individuals actually reflects their intelligence. And that's what I was looking for as well. Predictive validity is a degree of correlation known as a correlation coefficient between the results of a given measurement and an external criterion. For example, an investigator can validate an intelligence test by obtaining the test scores of a group of college students and then obtaining the grade point averages that these students achieved in their first year of college. The researchers then compute a correlation coefficient between the two sets of measurements. The resulting correlation coefficient is called the predictive validity coefficient. And of course, that's what I did with all of my instruments. I did a correlation coefficient with all my instruments. Establishing validity of criterion, one method relies on the agreement among researchers that a certain criterion is valid for evaluating a measuring instrument. This agreement is subject to tests of face validity and sampling validity. A different method involves determining the percentage of units of analysis that would be classified correctly by the instrument according to their known characteristics and expressing the relationship between the instrument's measured outcomes and the criterion in terms of percentage, units of analysis. Construct validity is established by researchers by relating a measuring instrument to the general theoretical framework within which they conduct their studies in order to determine whether the instrument is logically and empirically tied to the concepts and theoretical assumptions they are employing. You can come up with a lot of different questionnaires, and a lot of times they don't measure what you say they're going to measure. They are not valid because they don't measure what you want to measure. To demonstrate the construct validity of a measuring instrument, an investigator has to show that these relationships can be recognized and measured by their instrument. Measuring someone's temperature with a survey or written quiz has no construct validity, which makes a lot of sense. Your temperature is what? Is somewhere in the range of 98.6. How do you measure that? You use a thermometer. Giving somebody a quiz or a survey isn't going to give you very much information. And this has been one of the problems with COVID, because what they'll do is you go into the emergency room and you say, I think I might have COVID, I've got a cough, and I've had a low-grade fever for the last, for the last week, and they ask you, well, what has your temperature been? You say a low-grade fever. What is that? And you say, well, it just felt like I was hot, and that's not going to give them any information. Feeling hot and actually having a temperature are two totally different things. It's really hot where you are right now. It's pretty damn hot where I am right now. So a lot of times I sweat, and that, of course, if you're sweating, that means you probably don't have a fever. But you probably feel pretty hot, even though you don't have a temperature. Lee Cronbach and Paul E. Mayle describe the logical process of construct validation in the following order. A scientist suggests the proposition that an instrument measures a certain property, property A. They insert the proposition into a theory regarding property A. In working through the theory, the investigator predicts which properties should be related to the instrument and which should exhibit no relation to the instrument. He or she collects data that will empirically confirm or reject the predicted relations. If the anticipated relationships are found, the instrument is considered valid. If the predictions are rejected, the explanation for the failure to do so lies in at least one of the three possible causes. The instrument does not measure property A. The theoretical framework that generated the prediction is flawed. The research design failed to test the predictions properly. And of course, that's what we need to think about. And this is one of the reasons when I talk to you about your proposals, we need to figure out what instruments you potentially are going to use to determine if those instruments actually measure what you think they're going to measure. And that's one of the reasons why I've done so much interaction with you to get you to put your proposals together in a certain way. Because I mean, how well one of your proposals has to do with potholes. Well, how in the world do you determine what's a pothole, what is a pothole, and what isn't a pothole? Does it have to be a certain height? Does it have to be a certain width? Um, does it have to have a certain depth? These are all things that we need to determine. We need to make rules. Convergent discriminant conception of validity or multi-trait, multi-method matrix technique. This method derives from the idea that the different methods of measuring the same property should yield similar results. And this is, of course, one of the things that I did with my research. We were talking about resilience, and actually, there was somebody that did a resilience research right there where you are on the Navajo Nation. Um, they did resilience work looking at resilience that you have, and they used two instruments to determine how culturally aware people were. One of the instruments was exactly the same one that I used. The other one had to do with measuring cultural levels specific to the Navajo Nation, to individuals that were Diné. It was really kind of interesting. And so when I looked at my results, I determined that my results were very similar to theirs. And they said, what they said was that, of course, the one that's specific to the Navajo Nation is extremely accurate. And they got the same results from that cultural measurement that they did from the one that I used. And I used that as proof that I could measure the cultural level of American Indians. Of course, the group that I was dealing with were not Dene, but I used the same instrument that they did, and they said that it was accurate for the Navajo Nation, and I said, well, if it works for this group of American Indians, then I can say that it will work for another group of American Indians. Okay. Operationally, this means that the correlation coefficients calculated from scores for a given property measured by different instruments should be higher than the correlation coefficients calculated from scores for different properties measured by similar instruments. Measuring instruments should be examined for all three types of validity. First, evaluate theories that should serve as a foundation for the instrument, and that would be construct validity. Next, define a content population of items from which a representative sample is to be drawn. Finally, assess the predictive power empirical validity of the instrument by relating it to an external criterion, and of course, that's what I did. Reliability refers to the extent to which a measuring instrument contains variable errors. That is, errors that appear inconsistently between observations, either during any one instrument procedure or each time a given variable is measured by the same instrument. Um, I used to work in the lab, and in the lab, when you run a test, you need to make sure that your instrument is running properly. And we do that by using a standard and a control. We run the standards and we adjust the instrument so that the standards are accurate. And then we run the control to make sure that that we have adjusted the instrument correctly. And of course, you can't do that unless you have that type of an instrument. We're talking about a mechanical instrument. In medicine, we're talking about a mechanical instrument. But the reality is, and there are no standards or controls to use on a survey or a questionnaire. But we can. What we need to do is try to determine if this is actually reliable, if it's actually measuring what we say it's going to measure, and if it measures the same thing, if it measures things the same every time. If you measure a board with a tape measure and get 12 feet 6.5 inches one time and 12 feet 6.25 inches the next time, the tape measure has a variable error. Social science measures tend to be less exacting than physical measures, so variable errors are not only somewhat common but expected. Since variable errors are so common in social science measurements, the researcher must anticipate seeing an observed score and a true score anytime an experiment is done. In order to correct an observed score to a true score, the researcher must adjust the observed score using a statistical formula to calculate variance, and that's what we do. Um, we compare all the scores that we get. Sometimes we'll throw out the highest one, we'll throw out the lowest one, and we want to make sure that all the other scores are somewhere in between, somewhere in the middle. Estimating the reliability of an IQ test, we need to think about the discrepancy between observed scores and true scores for all persons who took the IQ test. To do this, we calculate a measure called the variance. This involves taking the IQ score for each person and subtracting this from each of these scores, the average IQ score across all persons who took the test. Since some of these quantities, x1 times, I'm not exactly sure what that means. That doesn't look like a formula to me. Will be negative and others positive. We then square these differences so that they are each positive. When we then add up these results and divide through the total number of test scores n, thus the formula variance can be written as that. That's the way it's done. So you take all the scores and you subtract them from the average score. Sometimes they're negative and sometimes they're positive. You square them, and actually, these. Don't look at these. That's a bad formula. It doesn't say anything. Anyway, so you take all the scores, you subtract them from the average, then you square all of those, which makes everything positive. You add all those together and you divide by the total number of scores. Actually, it's n minus 1, and that's your variance. That should be n minus 1. We must consider that variance can be calculated for each of the three n components for the distribution of observed scores, true scores, and errors. These three variances are then used to generate a reliability measure of IQ. We see that if our measure involves nothing but error, the measure of reliability will be 0. Conversely, if our measure is entirely devoid of error, the measure of reliability will be positive 1. Thus, reliability ranges on a scale from 0 to 1. In practice, all the researchers have to go on are observed measurements. The true component and the error component are unobserved. As a result, these components must be estimated. Generally, there are three methods to do so: the test-retest method, the parallel forms technique, and the split half method. Test-retest method derives directly from the conceptual definition of reliability. The researcher administers the same measuring instrument to the same group of persons at two different times, and then proceeds to examine whether the two sets of scores covary with one another. Error is defined as anything that causes a person to obtain a different score on the two tests. Now, there is a problem with the test-retest method. What you have done is you've cued the individual to what is on the test the first time you test them. So when you retest them, in their minds they already understand the test, and therefore it will skew the results. Does that make sense? Okay, so the first time you take a test, you've never seen this, you don't really know how the questions are put together. Maybe it takes you a little bit longer, you don't really do very well on the test. Then you go, wait a minute, this is what he did. So if you took the test right away, this isn't the retest. If you took the test right away, you do better on the test. Well, the reality is that you remember all of that when you retest, and of course, this is after they've done something to teach you something. And so then when you retest, of course, well, you've already been cued to all the questions. So it should raise the results. That's a problem. Oh, there we go. We're going to talk about it right now. A measurement taken on one occasion may influence or condition the measurements taken on subsequent occasions. Since many phenomena change constantly, it is possible that changes may have occurred within the period between the two tests, the measurement interval, thus lowering the obtained estimate of reliability. The test-retest method then may either overestimate or underestimate the true reliability of the instrument, and in many cases it is simply difficult to determine what has occurred. Parallel forms technique. The researcher develops two parallel versions of a measuring instrument. You probably did this when you took, usually the SATs are this way, the ACTs are this way. Many of the form tests that you take, there's an A and a B version. Both versions are given to the same group of persons. The researcher examines the covariation between the two sets of scores. With this technique, however, the problem arises as to whether or not the two versions of an instrument are in fact parallel. And that is the difficulty. The split method estimates reliability by treating each of two or more parts of a measuring instrument separately. Example, dividing a questionnaire into two parts, such as odd-numbered and even-numbered questions. Each of the two sets of questions is treated as a separate questionnaire and scored accordingly. The researcher then examines the degree of covariation between these two sets of results. Generalizability is the extent to which the research findings can be generalized to larger populations than were tested, of course, and applied to different settings than the setting for the initial research. And of course, this is a question that came up as far as my own research was concerned. I found that the group of American Indians that I measured had a high resilience level. Could I say that all American Indians have a high resilience level? And the answer is no, it's not really generalizable, mainly because we're dealing with a group of, I couldn't even say that, there are 7 reservations in Montana, and I did my research on one reservation. I couldn't even say the American Indians of Montana, the Northern Plains Indians. Of course, there are 2 different groups in Montana. One group is mountain tribes. They mostly eat salmon. They eat a lot of fish. And the others were plains tribes, and they eat mostly buffalo, or whatever they could find. So I couldn't say anything. I couldn't really say that. All I could say was this group of individuals, this is what I got. I couldn't even talk about the tribes because I didn't really, it was a sampling of 2 different tribes, actually 3 different tribes. But I couldn't really say anything like that. I couldn't really generalize that information. Okay, now we're going to talk about sampling and sample designs. The aims of sampling the population. The population is a complete set of relevant units of analysis or data. The sample is a subset of the population. So the population, if we were doing research on the Navajo Nation, it would be all the people on the Navajo Nation would be your population. The sample would be the subset of the population. In other words, the people that you actually did the research on the Navajo Nation. The parameter and attribute found in the population that can be measured. If you're looking at depression levels, you're looking at alcoholism levels, those are all parameters. You're looking at resilience. You're looking at IQ scores. These are all parameters. Sampling theory, the objective is to provide the basis for making accurate estimates of the unknown values of the parameters based on calculated sample statistics. To estimate unknown parameters accurately from known statistics, researchers have to resolve 3 major problems. The definition of the population, as we said. The example that I gave was the Navajo Nation is your population. The sample design, how are you going to sample these individuals? and the size of the sample. So you need a representative sample. What did I read the other day? The population of the Navajo Nation has gone up about 75,000 since COVID hit, and that's because people are who were off the reservation are moving home to be on the reservation. So the number of people on the Navajo Nation has actually gone up. So we're talking about 400,000 people. So what's your sampling size? Well, if you used 1,000 people, that would mean that if your sample size was 1,000, that would mean it would be 1/40th of the population of the reservation. The unit can consist of individuals. It can consist of communities, people with shared characteristics, cities, or even countries. Determining population poses challenges. Population has to be defined in terms of content, all voter eligible Hispanics, extent in the United States, time November 6th, 2012, the date of the 2012 presidential election. And all of these need to be defined. You need to explain to people what you're talking about. Sampling unit, a single member of a sampling population, a voter, a household, an event. Sampling units usually have numerous attributes, one or more of which is relevant to the research problem. A sampling unit is not necessarily an individual. It can be an event, a university, a city, a nation, or even documents. Finite population contains a countable number of sampling units. For example, all the registered voters in a particular city in a given year. Infinite population consists of an endless number of sampling units, such as an unlimited number of coin tosses. Give it to me straight, Doc. How long do I have to live? I'm afraid you've only got a few minutes left if you don't give me the map to the treasure. A joke. A sampling frame should include all the sampling units in the given population, but such information is rarely available. Instead, researchers usually have to use substitute lists that contain the same information, but that may not be comprehensive. And this was a problem when I was doing research. You can't find in the old days, you could go to the telephone book, and as long as somebody had a telephone, they would be in the book. So you knew that at least those people lived there. But now that everybody has cell phones, there isn't a list of people who live in a select town. In the old days, you could find that. Voter lists, if you can't get a hold of those because they are controlled and not everybody can see them. Somehow they do get a hold of them, though. The sampling frame for smaller studies may be based on telephone directories, city directories, or membership lists of private and public organizations. The researcher has to ensure that there is a high degree of correspondence between a sampling frame and the sampling population. Let's survey a representative group of males ages 13 to 17 with incomes over $13 million. That refused to change their hairstyle. I don't think that'll be a problem. And of course, they were talking about Justin Bieber. He was the only person between 13 and 17 who had $13 million who wouldn't change his haircut. The sampling frame must be evaluated for potential problems, incomplete frames, clusters of elements, blank foreign elements. Incomplete sampling frames are when sampling units found in the population are missing from the list. Solution might be to use supplemental lists. Example, if the population includes all the new residents of a community from a real estate listing, it might leave out renters. A city directory might be used to supplement the real estate listing. Clusters of elements occurs when the sampling units are listed in groups rather than individually. For example, the sampling frame may consist of city blocks, whereas the study focuses on individuals. One possible solution is for the investigator to take a sample of blocks and then list all the individual households in each of the selected blocks. The researcher then selects individuals from each household according to specific criteria. You can see how difficult all of this is. For one thing, finding out who's there. My wife worked for the census uh, in 2020, and she had a difficult time getting people to admit that they actually lived in select places. There are people that don't want to be found. Our neighbor, we can see the guy's house from our house. It's about a mile down the road. We can see that he's there, and we know that he comes and goes because we see his truck coming in and out. When she knocked on his door, he refused to answer the door. Finally, he came to the door, and she said, "I'm with the census. I need to take a survey. How many people live in your house?" And he said, "I'm not going to give you that information. I don't want anybody knowing that I live here." Finally, she convinced him. This is the deal. She convinced him to go ahead and give her the information, but he said, "I will only talk to you if you take this cat." He had a little kitten that he didn't want, and so she came home with a cat because this guy was being a jerk and didn't want to be counted in the census. As stupid as that was. Blank foreign elements occur when some of the sampling units in the sampling frame are not part of the research population, such as the case where the research population is defined as eligible voters, but the sampling frame includes individuals who are too young to vote. Solution: these cases should be treated as blanks and simply omitted from the sample. And of course, some of these people get to vote and some of these people don't get to vote. They may not be registered to vote, in which case they will be blanks as well. But these kids right here are definitely not voting adults. Representative sample. The essential requirement of any sample is that it be as representative as possible of the population from which it is drawn. A sample is considered to be representative if the analyses made using the sampling units produce results similar to those that would be obtained had the entire population been analyzed. And that's what we're always hoping for. This is one of the huge arguments during election years. We're getting all of these. We're getting all these statistics about how people feel about the candidates, all the polling that is being done, and the question is, who's whose sample is more representative? Is this representative of what's going to happen? One of the reasons that there are people that think that the election was wrong, that Trump should have won, but the reality was that all the polling told everyone that he was going to lose. Um, he squeaked out a victory the election before in 2016, even though he had 3 million less votes than Hillary Clinton. Well, this time he had 8 million less votes than Joe Biden. So it's a little confusing to me when the numbers are so obvious that people are still arguing with it. And so the question is the polling representative? Probability versus non-probability sampling. Probability sample distinguished by the ability to specify the probability at which each sampling unit of the population will be included in the sample. It makes it possible for researchers to estimate the degree to which the findings based on one sample are likely to differ from those obtained by studying the entire population. And this is one of the reasons why they give you statistics like yeah, Biden leads Trump by 5 points, plus or minus 3. That's that that gives you the probability that they're wrong. The non-probability sample, when there is no way of specifying the probability of each unit's inclusion in the sample, and there is no assurance that every unit has some chance of being included. It's used when a sampling population cannot be defined precisely or when a list of the sampling population is unavailable. The four major designs using non-probability samples, convenience samples, snowball samples, purposive samples, and quota samples. Convenient samples select whatever sampling units are conveniently available. This is what happens when people are coming, when they are polling people coming out of places where people vote, polling places. This is a convenience sample. Some people don't want to talk to them. They don't catch everybody. That makes it a convenience sample. Convenience sample cannot estimate the population's parameters from the values of the characteristic obtained from the sample. Usually they will go to polling places that are easy to access. Maybe there are more people at this polling place than at the other polling place. Maybe it's a nice part of town. In which case all of their results are going to be skewed to the population that they are actually sampling. Snowball samples often are used in combination with convenience samples as a way to sample what is called hard to reach or hidden populations, such as undocumented migrants who don't want anybody to know that they're there, female sex workers, prostitutes, and the like. The basic logic of snowball samples is to identify new sampling units, such as people, by soliciting information from existing sampling units. Researchers are able to increase the number of sampling units available to them in their study by asking them to bring in other individuals of the same kind. This is the way it was. This is the only way that you can deal with people that do things illegally, like people that are crackheads, people that use heroin. These people are doing things that are illegal, and therefore it's very difficult to sample people who are doing illegal things unless you can get them to agree to bring in their friends or for them to, anyway, it's not that easy. Purposive or judgment samples. Purposive samples require subjective judgment to select sampling units that appear to be representative of the population. Because it is usually difficult to determine why a researcher judges the sampling unit selected as being representative of the sample, it is difficult to determine the probability of the inclusion of any specific sampling unit in the sample. Purposive samples can still be successful, such as voter polling. Sometimes they're accurate. Yeah, well, it's really kind of interesting because each party will do their own polls. So the Democrats will say, "Well, we're ahead by 15 points," and the Republicans will say, "You're wrong. We're ahead by 5 points." And of course, what they've done is they've sampled their people that normally vote the way that they vote or the way they want them to vote, and mainly that's because these are the people they have access to. Quota sampling selects a sample that is similar as possible to the sampling population. For example, if it is known that the population being researched has equal numbers of males and females, equal numbers of males and females are selected for the sample. Groups characterized by specific variables such as gender, age, place of residence, and ethnicity are interviewed. 4 common probability sample designs: simple random sampling, systematic sampling, stratified sampling, and cluster sampling. Simple random sampling is a basic probability sampling design. Simple random sampling is incorporated into all of the more elaborate probability sample designs. Simple random sampling assigns to each of the sampling units of the population, denoted by the letter N, an equal and known non-zero probability in being selected. Systematic sampling consists of selecting every kth sampling unit of the population after the first sampling unit is selected at random from the sample unit of sampling units. If every 10th person is being sampled, then you would count off 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the 10th person would be part of the sample. Then you do it again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the 20th person would be this part of the sample. The first selection is determined by some random process, such as the use of a table or of random digits. Systematic sampling is more convenient than sample random sampling. Systematic sampling is easier to use with very large populations or when large samples are to be selected. Stratified sampling ensures that different groups of a population are represented adequately in the sample. All other things being equal, stratified sampling considerably reduces the cost of the research. Stratified sampling uses available information on the population to create a set of homogeneous groups based on variables of interest. So if the population was 70% white, 15% Hispanic, and 15% Native, then if out of 10 people, out of 20 people, they would have 14 white people, they would have 3 Hispanics, and they would have 3 Natives. Cluster sampling is frequently used in large-scale studies because it is the least expensive sample design. Cluster sampling involves first selecting larger groupings, called clusters, through random or stratified sampling, then selecting the sampling units from the clusters. The choice of clusters depends on the research objectives and resources available for the study. And when we say resources, the reality is a lot of this stuff is going to cost money. I was talking to a student the other day, and we were talking about surveying people about domestic violence on the reservation, and we were talking about, well, how in the world are you going to contact these people? And we are talking about mailing letters to everybody to explain the research, and then having them mail back a postcard saying, I'm willing to do this, and then mailing back again the survey materials. Well, all that costs a lot of money. I mean, if you're talking about 1,000, you're looking at initially you're sending out 1,000. You'll probably get back about 15%, which means you'll get 150 back. But you've put at least 2 stamps on that letter already, and you're talking about 1,000, and that's about $1,000 right there. So then you have to mail them all back, and you're going to probably mail back 150 of them, so that's another 50 cents a piece. So what is that? 150 times 50 cents is $75. So you've already spent $1,000 trying to get people to respond to you. It gets to be expensive. Fallacies concerning the necessary size of a sample. One is that the sample size must be a certain proportion, often set at 5% of the population. Well, if you're talking about the Navajo Nation with 400,000 people on the reservation, actually it's closer to 275, but let's say it's 400,000. If it has to be 5% of 400,000, that's what? 20,000 people? Is that right? 5%? Well, anyway. Yeah, I think so. 20,000 people. It's 5%. 1% would be 4,000 people. Yeah. Oh. Yeah. Yeah. So it'd be 20,000. Another one is that an adequate sample size is about 2,000 units. Still another misconception is that any increase in the sample size will increase the precision of the sample results. To determine proper sample size, researchers need to determine what level of accuracy is expected of estimates. That is the size of the standard error. And this gets really kind of interesting because if you're saying, well, I'm willing to have a select amount of standard error, then what you're saying is there's a 5% chance that my results are way off. People say, well, I only want 1% standard error, but that would mean that you'd have to sample too many people. And just getting that many people to fill out a survey is a bit of a trick. Standard error is a statistical measure indicating how closely sample results reflect or deviate from a parameter's values. It is calculated from the distribution of all the sample means about the mean of the total of those samples. Standard error measures the level of randomness in the sampling process. The standard error of the sample mean is an estimate of how far the sample mean is likely to be from the population mean. So I think I used 5% in my research. That meant that I needed to survey at least 150 people, and I had 105, I think. So my standard error was a little bit high, unfortunately. The mean and standard deviation are descriptive statistics. The standard deviation of the sample data is a description of the variation in measurements. The standard deviation of the sample is the degree to which the individuals within the sample differ from the sample mean. The standard error of the mean of the sample will tend to zero with increasing sample size because the estimate of the population mean will improve, while the standard deviation of the sample will tend to approximate the population standard deviation as the sample size increases. That makes absolutely no sense whatsoever. But they are descriptive statistics. We can take that to the bank. Um, Okay, so what we're doing here, let's say we've got 10 people and we want to find out what's the standard deviation. We want to find out how far along the spectrum all of these people were. So let's say you looked at 10 different people. So what you would do is you'd find the mean of all 10 of those people. Let's say the mean was 5. But you had some people that had a 1, you had some people that had an 11. So the idea was, well, how much did they vary? Did everybody get exact? If everybody got the same exact results, then the standard deviation would be 0, and that would be almost impossible because usually we're dealing with something that has to do with feelings. We have to do with attitudes. We're measuring something, depression level. How in the world could we find 10 people with exactly the same depression? The level of depression, resilience. How could we possibly find so many people with exactly the same resilience level? So what we would do, let's use resilience as an example. So what you do is you add up all the people that you sampled. In this case, I sampled 10 people. I got resilience levels that were between 100 and this is my instrument, 135 to 145. So the mean came out to be 140 right on the nose. Well, that means that the people got 145. Their deviation from the sample was 5, and the people that had 135, their deviation was -5. So what we would do, we take that 5, we take all the people that we're dealing with, and we would subtract the mean from all of their scores, and we would get the standard deviation. So the more variation there is in your sample, the larger your standard deviation is going to be, because they're not going to be that close to the average. It gets a little spooky if almost everybody gets exactly the same score. That would people vary a lot, and that would mean that everybody had exactly the same thought or the same level of thought, and that would be a little bit strange. In order to calculate a standard error, you need to calculate the standard deviation. We are trying to discover the standard error and standard deviation in the height of the starting 5 of a basketball team in centimeters. This is Gina. She's 170.5 centimeters. Sue's 161. Toy is 160. Freda is 170, and Ty is 150.5. The first thing we do is calculate the mean by adding the heights and dividing by the number of players. So there were 5 players, and if we add all their heights together, it's 812, which would mean that the mean is 162.4. We then need to find the deviation, and we do this by subtracting the mean from all the heights. So we subtract 162.4 from everybody's height, and we get all of these numbers right here. So you can see there's a deviation. 3 of the people were below the mean, and only 2 people were above the mean. but they were quite a bit above the mean. And the reason is because there were two tall girls on the team. There was one really short girl on the team, and the other two were right there in the middle. The next step is to square all of the deviations and add them together. And so we do that, and this is what we get. And as you can see, there are three people. Two people that are right around the mean, and then we have three people. Two people are really tall, and one person is really short, and that's Ty is really short. So we add them all together, get 272.7. We will now find the standard deviation of the starting five by taking the sum of the deviations squared, 272.7, and dividing by n minus 1, as I said before, where n is the number of units we have, 5, and minus 1 is 4. So we divide 4 into 272.7, and we get a standard deviation of 68.175. Oh, we haven't gotten it yet, have we? What did we get? Oh, we haven't gotten anything yet. To calculate the standard deviation, we will take the square root of 68.175, and that will be the standard deviation, which turns out to be 8.257. The standard error is the standard deviation divided by the square root of the sample size. The sample size is 5, and the square root of 5 is 2.236. The standard error will be the standard deviation, 8.257, divided by the square root of the sample size, 2.236, which gives you an answer of, so the standard deviation is 3. That's the standard error, 3.693. The standard deviation is 8.257. The standard error is 3.693. If each player were the same height, the standard deviation would be 0. The larger the sample, the closer to 0 the standard error becomes, because it makes the outliers less mathematically important. Yeah, I think I figured this out. This is a pretty short team. This is in centimeters. Oops, this is in centimeters. So the lady that's 150.5, let me get out of this screen. Let's see how tall that is. 150.5 centimeters to inches. And the answer is, that's 59 inches. That's what? 59, 60 inches is 5 feet. So she's below 5 feet tall. How about the other girls? Wait a second. 170.5. Let's see how tall she is. Okay, inches. So she's 5'7". So one girl was the tallest girl was 5'7", which is my height, and the other girl was under 5 feet tall, which is my daughter's height. So there you go. This is a pretty short basketball team. Come on, there we go. And that's how it's done. Confidence interval is how much uncertainty there is with any particular statistic. Confidence intervals are often used with a margin of error. It tells you how confident you can be that the results from a poll or survey reflect what you would expect to find if it were possible to survey the entire population. Confidence intervals are intrinsically connected to confidence levels. A confidence interval for the mean is a way of estimating the true population mean. Instead of a single number for the mean, a confidence interval gives you a lower estimate and an upper estimate. For example, instead of 6 as the mean, you might get 5 to 7, where 5 is a lower estimate and 7 is the upper estimate. A normal curve is a theoretical distribution of great significance in the field of statistics. Some of its major properties are it is symmetrical and bell-shaped. The mode, the median, and the mean coincide at the center of the distribution. The curve is based on an infinite number of observations. The single mathematical formula describes how frequencies are related to the values of the variable in any normal distribution. A fixed proportion of the observations lie between the mean and fixed units of standard deviations. The normal curve, if a given sampling distribution is known to be approximately normal, we can infer that about 68% of the sample estimates it comprises will lie between its mean and the one standard error, and about 95% between its mean and two standard errors. Estimating the size of the sample to be drawn, recall the formula for the standard error of the mean, whereas S equals standard deviation of the variable under study and N equals sample size. Inverting this formula, we then have N equals S squared over SE squared. If the sample size turns out to be too large relative to the population, the finite population correction is added. In this case, N over N is added to 1. The final sample size is thereby calculated thusly. Decisions concerning the sample size. First, researchers must decide how precise they want their sample results to be, how large a standard error is acceptable. Second, they must decide how the results will be analyzed. Third, if more than one variable is being examined, the researchers should decide whether a sample size satisfactory for one variable is adequate for other variables. Okay. Sampling theory is concerned with the error introduced by using a sampling procedure. In survey research, the most common error is non-responsive error. Non-responses are defined as observations missing for reasons such as the refusal to be interviewed, like my wife had with the guy in the census, and actually she ran into probably 10% of all the people that she tried to count refused to be counted, as strange as that may seem. And this is in Iowa. We're not talking about, well, I don't know. We are talking about some interesting people, I guess. Non-responses are defined as observations missing for reasons such as a refusal to be interviewed, an individual's absence from the home, a misplaced form. Non-response can introduce substantial bias in the findings. They did research a number of years ago looking at, it was a survey that was in National Geographic magazine. And as it turned out, they had hundreds of thousands of responses because there are hundreds of thousands of people around the world who read National Geographic magazine. But there was a bias to it. And there were two biases. One of the biases had to do with the people who read National Geographic magazine. First of all, they had to have enough money to buy, to read National Geographic magazine, to subscribe to it, and that was a special population. And then the people who take surveys are a special population. So both of those aspects made the results biased, as strange as that may seem. You're not getting a random sample because you're only dealing with people who read National Geographic magazine. You're not getting a random sample because only people who fill out surveys are the ones that took the survey. There are people that represent a different type of person who don't fill out surveys. The amount and kind of bias is related to the following conditions. The greater the rate of non-response, the greater the bias introduced. And of course, this is information that you have to give when you're writing up your research. How many people did you try to survey? How many non-responders did you get? The response rate can be calculated as follows. And there you go, where R equals the response rate and N equals the sample size. The seriousness of the bias depends on the extent to which population mean of the non-response stratum in the sample differs from that of the response stratum. And of course, that's difficult to tell because they didn't actually take the test. Each of the following types of non-response influences the sample results in a different way. Uninterviewables are people who are illiterate, or have language barriers. Not found, people who have moved or are inaccessible. Not at homes, people who are out when the interviewer calls but are reached later and their responses are subsequently added. refusals, people who refuse to cooperate or to answer all the survey questions. And that is the end of chapter 7 and 8. So the two things that I want you to put in your proposal this week is your measurement error. Are there any intervening variables? Can you think of any outside variable that you're not measuring that would potentially skew your results or make it inaccurate? It's going to take when you're doing the research, all of these things come flooding into you, and you go, "Oh man, why didn't I even think about that?" And that's what I want you to think about. I want you to think about possible errors that you have made, or I have made, or we have made um, in putting your proposal together. What are some of the things that might potentially skew the results? Traditionalism uh, versus people that are more attuned to the dominant society, the Native American church, Christianity. Are these factors that are going to change? Are these variables that might change the way people see things? It's the summertime. We're talking about summertime rather than winter. There are certain things you can do in the summertime that you can't do in the wintertime. I'm talking about traditional ceremonies here. Uh, Canalda. Can you have a Canalda in the wintertime? All of these things. I'm thinking of the squaw dance, but I'm not real happy with that term. I know it doesn't bother anybody probably but me. Uh, that's you can only do those in the summertime. So that's what we're looking for. We're looking for measurement errors. What else are we looking for? The sample technique. So how in the world are you going to do this? You're going to put a survey together. How many people are you talking about? And that's what I want you to put in this week. I want you to put in possible intervening variables that might skew your results and how you're going to do your sampling. Okay? And that is the end of the lecture.